Okay, in this video I'm going to record conditional probability and multiplication rule. So what we are going to cover today: conditional probability, independent, dependent events. We will cover multiplication rules and use multiplication rules to find conditional probabilities. So conditional probability is the probability of an event that will occur if another event is already occurred. For example, rainbow will happen only when rain happens, right? We have here conditional probability. Or let's say, what another case? I will go to the beach if the sun is shining, right? So sun has to be there, condition, so I would go to the beach. Okay. Well, we denote with a vertical line here, which means B will happen when event A is given. So let's find conditional probabilities. Example, we are going to deal with cards. So there are total 52 cards in the deck. So 2 cards are selected in sequence from a standard deck. Find the probability that second card is queen given, this is important, given that the first card is a king. So given this, it's a conditional probability. So what we are going to do, we know that first card is a king, right? And it says the king is not replaced. First of all, what is the probability of the king? There are total 4 kings, right? In entire deck. So probability for the king, it's gonna be well, it's not here. Probability for the king, it's gonna be 4 out of 52. Yes? All right. Now, king is not replaced, which means if king is not replaced, we put on a side. So out of 52 cards, we will have left how many? 51. So what's the probability that second card is a queen? How many queens we have? 4, correct? Here it is. But 4, it's gonna be among 51 cards, not 52, because a condition was the first card was a king and it's not been replaced. So therefore will be 4 out of 51. All right. Second one. The table shows the result of study in which researcher examine a child's IQ and the presence of specific gene in the child. Find the probability that the child has high IQ. Here it is, high IQ, given that the child has a gene. When it says given, that means we are going to look for high IQ among given gene. Okay? So high IQ among present gene on the table, right? How many the people have total present genes? 72, right? And how many have high Q among present gene? 33. So the probability is going to be 33 out of 72. That's why I was underlying when it says given, that given become your total. And what is given? The present gene is 72 total. Therefore, high IQ, we are going to look 33 out of 72. Okay, that's a conditional probability. Condition is gene is present. Independent events. Well, two events that are independent, they can exist independently. For example, sun and wind, rain and sun, they are independent. A dependent one is the event that depends on another event. Let me take the same rainbow. It depends on rain, right? Rainbow will not happen if rain will not happen, right? Okay. So let's get example of independent and dependent events. Selecting a king from a standard deck, not replacing, it's crucially important, not replacing, and then selecting a queen from the standard deck. So when we select king from the standard deck, it's gonna be what? 4 out of 52, right? Selecting king from the standard deck. It's gonna be 4 out of 52. And then not replacing, which means it's gonna be left for 51. Wait a minute. What is this happening? Selecting king from the standard deck A, not replacing king, and then selecting queen from the deck. So if we take king, 4 out of 52, we are not replacing, which means gonna be left total 51. Then the queen, it's gonna be 4 out of 51. This is wrong here. Not 52, but 51. Okay, here it is. 4 out of 51. This one is not a queen, but king. Oh, I see what's happening. Okay. Let me see. So, this is probability of the king. This is 4 over 52. And then second card is a queen, given first card is king. Okay, so these two events are dependent because the king affects the probability of queen, right? If we wouldn't have selecting king and right away would select the queen, we would have 4 out of 52, right? Probability for the queen. But because we select the queen after selecting king and not replacing, therefore this event is going to be dependent. Now here, tossing a coin and rolling a die. Now these two events are independent. There's no way they can affect each other. So probability of tossing a coin, how much it's going to be? 1/2, right? Rolling a 6 head on. Okay, let's make things clear. Tossing a coin and getting a head. So it's going to be 1/2, right? And then rolling for the coin probability. And then rolling a 6-sided die and obtaining a 6. So what's the probability of obtaining 6? It's going to be 1 out of 6. So this 6 is not the value of 6, but because we have total 6 sites. So they are independent. Okay? So these two events are independent because this has nothing to do with this one. Okay? So multiplication rule. One thing you need to know, every time when it's mentioning and, it's converting mathematically into multiplication. Okay? So every time we have and. Let's look at the event. Here it is. Two cards are selected without replacing the first card from standard deck. Find the probability of selecting a king and then selecting a queen. So it's sequence. So selecting a king, which will be 4 out of 52, and, which means we turn into multiplication, selecting a queen. We don't replace the king, so for the queen will be left 51, right? And times 4 out of 51. This is probability of king. This is probability of queen, right? Okay. Next one. Sorry, I stepped aside. Oh, here it is. So let me clean this so you can have it anyway. So 4 out of 52 times 4 out of 51. And will be 0.006. That is approximately 0.6%, right? By two positions, 1 and 2, meaning multiply by 100. 0.6%. Next one. A coin is tossed and die is rolled. Find the probability of getting a head, which gonna be 1/2, and then tossing a coin, which gonna be 1/6. And it's exactly, what's gonna happen right here. Probability of head and 6. Probability of head is 1/2, and then probability of rolling a 6, it's 1/6. So we get, how about 8.3%. Moving by two positions, 1, 2, and get 8.3%. Okay, the probability that a particular knee surgery is successful is 0.85%. Find the probability that all 3 knee surgeries are successful. Can I replace it with find the probability that and the first surgery is successful and the second is successful and the third is successful? Can I do that? Yes, I can. So first one, second surgery, third surgery. First surgery success is 0.85, and second surgery success 0.85, third surgery success 0.85, and we multiply all 3 of them. There we go. Probability of 3 surgeries are successful. 0.85, 0.85, 0.85 will be 0.614, which is approximately will be 61.4%. Okay? Okay, moving to next topic. Find the probability that none of knee surgeries is successful. If 0.85 is successful, then not successful, it's going to be 1 minus 0.85, right? 0.15, yes? So it's a kind of complement. If 85% is successful, that means 15% is not successful. Which means none of them. So all three, first surgery, second surgery, third surgery, it's going to be 0.15, 0.15, 0.15. And the result is going to be all three multiply, because and first one not so successful, and second one is not successful, and third one was not successful. I would fire such surgeon. Okay. So we get 0.003, which is approximately 2 positions, 0.3%. All right. Well, we don't need to do this. Moving to next one. This is too long of the story. And we are done with this case. Okay. Well, I will record, next I will record 3.3.